Yes, so the next presentation is entitled Characteristics of FRP Pretensioned Concrete Beams After Long-Term Exposure, and it's going to be presented by Hirofumi Watanabe. Correct? Yes, please come.
Thank you very much for your kind introduction. I'm very pleased to speak to you about characteristics of FRP pretension concrete beams after a long-term exposure. This study is supported by ACC, Association for Advanced Composite Technology on Construction Field. Fiber reinforced polymer FRP boards have attracted a lot of interest as an alternative reinforcement material for concrete structures due to their high strength, lightweight, non-magnetic nature, and corrosion-free properties. Since 1988, FRP has been used in over 500 structures throughout Japan and more in the world for reinforcing materials. However, it has been pointed out that the bond between FRP and concrete could be a potential problem due to the difference between the thermal expansion coefficient of FRP and that of concrete, and the fact that organic fibers are hygroscopic. The objective of this study is to better understand the degradation over time of pretension concrete beams subjected to repeating drying, wetting cycles and variations in temperature under natural environment. This study has begun in 1997 at first planning production of specimens. Initial loading before exposure and beginning of exposure in 1999. And since then, 3 loading tests, initial and the second and third, and chloride ion inspections have been taking place. And some of the specimens are still in exposure. We be 2030 amount of age 32 years. The parameters of this study are the material of tendon, the exposure site, and the exposure time. The extent of degradation was assessed through static testing at the end of the exposure period, and observation of the onset of rusting in case of steel reinforcement. The letter of ACS is a material of the tendon, aramid, carbon, and steel. Letter of IT is the exposure site. I is the express zone, and T is the inland. Control 1, 2, 3 indicates exposure time. Control is a non-exposure and destroyed at its age of 2 months before exposure. Number 1 destroyed at age of 3.7 years. Number 3 is destroyed at age of 70 years. And number 2 is still in exposure. This photo shows exposure site. Left the splash zone. There is a hole in the rock through to outer sea, and when the weather is bad, spray blows to specimens hardly. Very severe environment. And right inland, in ordinary environment, no salt and no heavy precipitation. This table shows the properties of the materials used as tendons. The aramid FRP is Technora, and the carbon FRP is CFCC. In this table, the Young's modulus, or a ratio of 1 to 2 to 4 for aramid, carbon, and steel. The thermal expansion coefficient of FRP is about 0 or even negative. The upper table shows the mixture proportions of the concrete. The nominal strength is 50 megapascal and had a water cement ratio of 37.2%. All specimens were cast using pretensioning method. The initial pre-stress for all specimens was 62% of the guaranteed tensile capacity. A figure in left shows the compressive strength of concrete at different ages. It is apparent that compressive strength increases substantially over time compared with the initial value. The figure in the right shows the shrinkage strain of concrete observed using strain meters. At the age of 17 years, an average shrinkage strain of approximately 860 micro was observed. This figure shows the dimension of specimen and height of 200 millimeter, width of 150 millimeter. In the left section, FRP reinforcement had two tendons at the top of the section and two at the bottom. Steel reinforcement in right section has one steel strand each at the top and bottom. The stainless steel stirrups are arranged around the tendon at a pitch of 30 millimeters. This figure shows the loading method. The length of the specimen is 2 meters, the support span at 1.8 meters, and shearing span is 0.8 meters. The initial load before the exposure was applied to introduce brake cracks at the age of 2 months, equivalent to about 60% of the FLEXURAL capacity. At the age of 3.7 years and 17 years, a load was applied again. The crack reopening load was observed using crack gauges. And a comparison made with the pre-cracking load observed at initial loading test. Now I speak about the results of this study. This figure shows the flexural modes of the specimen in case of aramid approximately the same time of the failure of the concrete and tendon. In case of carbon, preceding the fracture of tendon. In case of steel, concrete failure after yield of tendon. These results were consistent with that of the FEM calculations by applying a fiber model using the concrete compressive strength with the age of 2 months and a tensile strength of the prestressing tendons. This table shows the flexural moment capacities and deflections. In the table, calculation is a result of FBM control. Control is a non-exposure ages, exposure site, and materials. To notice the flexural moment capacity, the values have no difference. They had a coefficient of variance less than 2%, and it matches nearly perfectly with the calculation. And in other words, aging degradation caused by the sprays of seawater and temperature changes do not occur in 17 years. This figure shows the flexural moment displacement diagrams of each materials. Control is a non-exposure. Number 1 is at age of 3.7 years, and number 3 at the age of 17 years. The curves overlaps and become thick. From this point, it can be said that there is no difference by age. Next, the calculation of the effective prestress. The effective prestress is calculated using these formulas. Effective prestress of tendon is a prestressive stress at introduction minus a sum of the reduction of stress of tendon through relaxation and reduction of stress by concrete shrinkage. This gamma is the apparent relaxation rate, including the environment of concrete shrinkage. This table shows the result of calculation. Prestressing stress, concrete shrinkage, apparent relaxation rate, and calculated effective prestress of tendon. The concrete stress by effective prestress were approximately 4 Newton per square millimeter, and cracking moment and crack reopening moment were back calculated using this value and concrete tensile strength measured at the age of 2 months. This table shows the comparison of the cracking and crack reopening moment. The experimental is the measured value by loading tests using crack gauges attached to the cracks. And calculation is the value by a previous back calculation. The measured values were larger than the calculated value, and it became clear that the relaxation rate chosen for the material test was relative appropriate value for the specimen with long-term exposure. In this study, a chloride ion concentration is of concrete exposure in the splash zone were inspected in the age of 3.7 years, 12 years, and 17 years. This figure shows the measured chloride ion concentration. The left side is the top of the section and right the bottom. The chloride ion concentration was measured over 5 kilograms per cubic meter at the tendon located 35 millimeter from the surface of the specimen, 35 millimeter at this point. And after 12 years of exposure. However, during the demolition investigation, after failure following 17 years of exposure, almost no rust was found in the steel strand, and the structure can be considered sound. Therefore, we decided that left specimens will be exposed again in order to clarify the difference of durability between each materials of the tendon and the facilities at the shore side of back sea and inland. To the years of the 2030 amounts age of 32 years. And conclusion. In an effort of better understand the durability of FRP bar in a severe environment, a long-term study had been undertaken using the tendons made of aramid and carbon fibers and steel strand and pretensioned concrete beams. As a result, it was confirmed that there are no observable or detailed relation in terms of the flexural capacity on account of the 17 years of exposure. The pre-cracking of the pretension beams at 60% of flexural capacity does not have a negative influence on tendons exposure at the splash zone for 17 years. Although it was assumed that degradation will occur when the steel strand is exposed to the splash zone after roughly 15 years, it became clear that if dense concrete is used, there is no degradation, similarly to FRP tendons. Finally, this study was undertaken by the Institute of Industrial Science, University of Tokyo, through funding from ACC. That is all for my presentation. Thank you very much for your kind attention.
Thank you very much, Very interesting study, very important study. One of your conclusions was very positive, that even after 17 years there was no considerable deterioration in pre-cracked members. We often relate deterioration and limit crack widths therefore. So my question is, I apologize if I missed this data. Did you have also measurement on crack widths? So you mentioned that elements were pre-cracked. Did you have measurements on crack widths?
What widths of cracks? I think in this study, crack-wise, average crack-wise is 0.5 for aramid and 0.3 millimeter for carbon and steel at 60% of FLEXURAL capacity, and so normally sorry. With aging, some crack-wise is no changes in many times that loading, no failure. Thank you.